Hi there. Okay, this video is on the third segment of magnetism. Remember, the first segment was on the Lorentz force law, and this was the force that was due to a charge that's placed in a magnetic field, and that included current carrying wires. In the second segment of magnetism, we studied what happens when you take a current and create a magnetic field. So we studied how currents actually make magnetic fields form, right? So we looked at, hey, if I have a current already, then can I make a magnetic field out of that? And the next logical question is, hey, if I have a magnetic field, can I make a current with that magnetic field? And so that's what we explore in this new segment. So I'm going to write this as a question because that's really what we're here to answer. So the way that this went down was basically the setup that I have in front of you is essentially it's just a hoop. We have managed to coil it around a bunch of times. But if we create this hoop and put a device on there that's an ammeter or a really sensitive ammeter, which we call a galvanometer, then when we look at the galvanometer, it tells us, hey, how much current is flowing in which direction. So we really want a sensitive device to tell us there's nothing else attached to this wire. It's just attached to itself. Is there a way that I can take magnetic fields and you shoot them at this thing or whatever and make a current? So the first experiment was about taking an electromagnet. So they put an electromagnet next to the thing and ran it, right? And asked what happens if I turn this on right next to the thing and leave it there and carefully measure whether there's a current. And so they kept getting more and more sensitive apparatus. There was some disturbances, but they couldn't find anything if they just left this on. So when they turn it off, then they'd see a jump in the needle. Then when they turn it on, they'd see a different jump in the needle, and they turn it back off, they'd jump in the needle. They turn it on, they get a different jump in the needle. So they started asking, wait a second, well, this has to do not with the magnetic field itself, but with actually changing the state of the magnetic field in your hoop. So we're going to call this a hoop. It's a solenoid, but it's basically made out of a bunch of hoops. So what you're going to do as a student is you're going to investigate the middle of this hoop. You're going to actually be the middle of the hoop. And remember, this is not a hoop that's connected to a battery, so you just have some hoop. It could be like a metal hula hoop, or it could be like a metallic border to a garden. It doesn't matter. The window frame, any metal that basically forms an entire circuit, right? But there's no battery attached to it. So that's what we have here. And what you're going to do is be that hoop and ask, what's going to happen to me and how am I going to make a current? Okay. So what I really want you to do is answer 3 questions in order to figure out whether current will flow, and if so, in what direction. Now, strictly speaking, this is Lenz law that we're discussing now, which is the responsiveness of hoops to the change in magnetic flux. So what we really are asking about is if we were to take magnetic field and apply it here, so we'll apply some magnetic field in this direction, how much magnetic field is going through our hoop, how many field lines. Now you remember flux, hopefully from Unit 1. I exposed you to flux so that you would, not really because it's super useful in electrostatics, but because it's super useful in magnetics. So it helps us to understand how to anticipate these things. Really, it's flux that we're talking about here. So if we have magnetic flux, remember this is not the same as electric flux. So there's electric flux and then there is magnetic flux, and we're interested in magnetic flux. Our magnetic field is going from left to right here, so we're going to ask 3 questions. Here are 3 questions. Now I already gave you 1 through 3s for something else, so I'm going to give you A, B, C for this. The first question that we're going to ask is, what direction? And by that we mean, what direction is the flux? And in our case here, it's pointed from left to right. But you always have to re-ask that question in every scenario. The second question that you're going to ask is it increasing or decreasing? What do we mean by that? Well, we have 3 field lines here. If I were to up the magnetic field, step on the pedal and increase this, right? A lot of field lines in here. If I really increase that, then what I've done is I've increased the magnitude of the field. So we need a direction and we need a magnitude. And then really you're almost finished. The third thing that you need to ask is, what are you going to do about a hoop? Now, the principle behind this, behind our third question, is that we want to prevent change. Now, you there in the middle of the hoop, what would you do about it? What would you do about the fact that you have a magnetic field that has been changing? If you had 3 field lines going through and they stayed 3 field lines, you're happy as a lark, no problem at all, right? But what you don't like, what you won't tolerate as a hoop, is change in magnetic flux. So now that we have increased this, we would go through and ask our questions and say, okay, in this case, we know that we're moving from left to right. We know that we're increasing. So not only are we pointed from left to right, but we're increasing, pointed from left to right. So the thing you're going to do about it, I'm going to get a whole different purple color here so that you'll see that we have 2 different magnetic fields that are going to be involved. What you're going to do about it is increase magnetic field this way. Why? Because you're trying to restore it. If we had 3 field lines and now we have 5 field lines, you're going to try to make 2 to cancel some of that so that you can go back to the 3 lines. Now, this is not a very powerful effect, and so you will never really truly cancel, but you sure will try. So you, as the hoop, or you can imagine yourself as that little green dot if you want. There's nothing actually there. Just imagine like a really grumpy, grouchy little man in the middle of the hoop that's, I can't tolerate change, right? So when you see magnetic field lines increasing to the right, you say, well, I have to do something about that. So you create a magnetic field to the left. Now, how are you going to accomplish that? Well, we can go back to what we looked at in Ampere's law. In order to make this field, you're going to need to create a current in the hoop, right? This is just a solenoid. But what you're doing is, instead of a battery, you're actually allowing nature to create that electrical current. Now, if you studied your right-hand rule, you would know in order to get that magnetic field, you have to have a current that goes this way in our drawing, right? We would need it to be going up in the front and down in the back in order to produce a magnetic field. So this is induced current, and this is induced field. If you want, you can refer to this other field as like an intruding field. It's fine. Okay, so the premise here, and the thing that I want you to be clear about, is that you were sort of an innocent bystander hoop, right? Just standing there waiting for change so you can fight it. And then the external field here created a change in the environment, and you responded as a hoop. Okay, let's look at some more examples of that. Okay, let's say we created some field using some external device here, and our device originally is causing magnetic field to go from this right hoop to this left hoop. Okay, and remember, you're the hoop in the middle here, who's just an innocent bystander, right? And you're going to experience the magnetic flux that this external device is creating, and then someone switches off the device. Okay, switch off. At that point, then you need to ask these three questions to determine what direction the current is going to flow. And the way that I want you to look at the current flowing here is, in this galvanometer, is it flowing from the left to the right here, or from the right to the left? Right. That way, it's easier to talk about where it's flowing in this hoop. So, first thing that we need to do is answer the first question. What direction is the magnetic field and flux that is intruding upon you, the hoop? It's going from right to left. Now, is it increasing or is it decreasing? Well, at first we have 3 field lines here, and then when they switch this off, at that point you're not going to have any field lines, right? It's just going to go from 3 to 0. So that means that it's decreasing, right? Now, what are you going to do about it? Well, as the hoop, you used to have field lines going from right to left. Now you don't. So your first response is going to be to create field lines going from right to left to make up for the loss. In order to do that, you need to induce a current, and you can take that current and go, let's see, from the left side of your galvanometer to the right, meaning that the current will go up in the front of the hoop and down in the back in order to produce the magnetic field necessary to compensate for the loss of this external field when it was switched off. Let's try another one. Let's consider a bar magnet. Now you remember that you have field lines leaving the North Pole and exiting this, leaving the North Pole and entering the South Pole. So now if we were to take our bar magnet and we were to, let's say, throw it, give it some velocity toward your hoop, so actually start throwing it through the hoop. As it gets close to the hoop, as it's nearing the hoop, I want you to pause the video and guess which direction the current is going to go in our hoop. Is it going to go this way or this way? To the left or to the right in our meter? Okay, so I'm going to go ahead and assume that you paused the video. Let's work through this. We ask our questions one by one. We'd say, okay, what direction is the flux? It is from right to left. Oh, it's okay. What is it, increasing or is it decreasing? So we know that we have a couple of field lines that are managing to make it into the hoop, and most of them are missing. As the magnet gets closer and closer to the hoop, then you get more field lines that are actually getting enclosed in the hoop, right? By the time the magnet is in the hoop, all of the field lines will actually manage to go through the hoop. So we are increasing the flux. So if we are going from right to left and increasing our flux, what are you going to do about it? Pointing to the left, increasing, means that you need to oppose that increase in flux by making some flux to the right. So we are going to create a magnetic field that way. In order to do that, then you need to make a current that goes this way. Okay, so hopefully you worked through that correctly, or if you didn't work through it correctly, hopefully you understand now why not, and if you have trouble with that, then let me know. So this is our first video, and I want you to keep practicing on this, ask questions, and let me know where you're tripped up. If you guys want another video on this is the hardest topic in the whole semester. So if you want another video on this, just y'all tell me what you're interested in, and I'll produce another one on this topic. In the next video, we're going to study the mathematics of Faraday's law.